Hello, welcome back. So, we are just left with one small chapter that's called kinematics, and the reason why it's the last chapter is because uh, this chapter is a small extension of calculus, and it basically expands upon the physical aspect, the physical aspect of differentiation, the real life aspect rather. And so it is implied that, of course, you should already know calculus, and if you've forgotten it a little bit or if it's a little shaky, I would recommend that you go back and watch the calculus series. Right, so the basic thing to know in kinematics, the only new thing to know in kinematics is the following relationship, that displacement, if you differentiate the displacement with respect to time, it gives you velocity. And then if you differentiate velocity with respect to time, it gives you acceleration. Right, so this is literally how they are defined. Velocity is how much displacement changes with some change in time, and acceleration is how much velocity changes with some change in time. Now, the reason why we are differentiating this, so say for example, you might have probably come through this before, but let's say this is my displacement, this is my time, and let's say this is my graph, or let me break it up like this. Now, in this graph, if you're given the equation of this line, well, you don't really need to apply calculus because it's only a straight line, so it's easy to calculate its gradient. But let's say instead of this, my graph is much more complicated. Let's say it it increases like this, and then it goes down, and then something like that, right? Now, this sort of situation is exactly where calculus comes into play. When you have a curve and you want to find the gradient at certain point, or the closest approximation to gradient, you use calculus. So if I have displacement and then I differentiate it, I get velocity, and then if I differentiate further, I get acceleration. And of course, all of these are with respect to time. Now, one thing to notice here is that uh, is the interpretation of positive and negative signs. So, if I look beyond this point, the displacement is negative, and if I were to take its differential, this is some point at which the gradient will be zero, and then the gradient is also negative, right? And so what negative and positive really mean is that they're indicating direction. So by convention, what we really take is that we say that the right hand side is the positive direction, and similarly, if we're somehow including the vertical axis, if you go up, then that's positive. So let's say if my displacement is positive 8, then that really means that between these 2 points, let's say this point A, point B, if you want to go from point A to point B, you will go to the right 8 units. Similarly, if velocity is, let's say, coming out to be 3, then that means your displacement is increasing to the right 3 units per second. If I had, let's say, displacement of -10, then that would mean that if I want to go from point A to point B, I would go in the left direction. Right? And similarly, if the velocity was negative, then that really means that the increase in the change in displacement is happening on the left hand side. So let's go ahead and try a question out from, let's say, exercise 16.1, question 1. It says a particle moving in straight line passes through a fixed point O. So there's some point, it's labeled O. Its velocity is v meters per second. So when it's currently at point O, its velocity is v meters per second. Sorry, I misread the question. It says that uh, its velocity v meters per second t seconds after passing through O is given by this certain formula. So they're saying that velocity is given by 50 over 3t plus 2 squared. Part A is to find the velocity of the particle as it passes through O. So this should be 3t plus 2 squared. Okay, so when it is at O, this certain time frame is indicated by by t equals 0. This is what is t equals 0. So if we simply input t as 0, this will give us 50 over 2 squared, and that would be 12.5. Next, it asks us find the value of t when the velocity is equal to 0.125 meters per second. So if this is the formula for velocity and I want it to be equal to 0.125 seconds, then I will simply cross multiply, and this would be 0.125 times 3t plus 2 squared. And then part C is actually when the calculus part comes into play. It asks that find the acceleration of the particle when t is equal to 1. So I told you that the acceleration is the differential of velocity with respect to time. So what we really need to do is find dv over dt, and we need to find that at the point t equals 1. So if we apply the quotient rule, that is if u is 50, then u prime would be 0. If v is 3t plus 2 squared, then v prime would be 2 times 3t plus 2q, no, just to the power 1 multiplied with 3. And then we can simply do vu prime minus ue prime, and we get minus 50 over 6 times 3t plus 2. And we want to find the acceleration when t is equal to 1. In other words, minus 50 over 6 times 5, and this would turn out to be, well, we can do minus 10. It will turn out to be minus 10 over 6, right? And minus 10 over 6 basically means that the velocity is increasing but in the left direction. So if I go up over here and I make, let's say this is some time t, and let's say this is some time t, let's say this tx and this is ty. So if I'm imagining what's happening to that particular object, when its gradient is positive, it is moving to the right, right? And it keeps on moving to the right until it reaches some time tx, right? When it is at tx, the gradient becomes 0. Before it was positive, then that means that the displacement is increasing, right? You can also see from the graph the gradient is the value of s is increasing until it reaches some point tx, and then after tx it is decreasing. So we go back, and then at ty it is back to 0. It started from 0 and it is back to 0. So it will, this point in time is ty, and then it continues to go over here, right? And so now we can move on to the other half of kinematics, and that is integration. So we discussed that the differential, if okay, so if you want to go from displacement to velocity, you differentiate, and then from velocity to acceleration you differentiate. If you want to go the other way, let's say from acceleration to velocity, you would integrate, and also from velocity to displacement you will also integrate, simply because integration is literally the opposite of differentiation, is the antiderivative, right? And also one more thing I would want to discuss here is that we can see here that if we want to find the integral function, let's say this something and then we get something else, there's a particular reason why we have to include a plus c over here. Let's say I integrate the velocity function. Now integrating the velocity function will basically tell me the change in velocity, right? If I plug in any number, it will, if we don't add any plus c, we are assuming that it is plus 0, right? The interpretation of displacement being 0 is that we look at some point, and this is sort of our marked point or starting point. This is the point from which we measure displacement. If this is 0, then that really means that we are starting from this point. Now, if we integrate, let's say with some limit, let's say 3 to 5, over here we don't have to put a plus c, because what this will really do is it will tell us how much the displacement change between 3 to 5, between the time 3 to 5, right? So if you want the displacement, if you want the final displacement, then that would be the initial displacement plus the change, which would be the integral, right? So to put it in formal words, the integral of acceleration with respect to time is velocity, and the integral of velocity with respect to time is displacement. Okay, so let's go ahead and try the question, that is worked example number 5. It says a particle moving in straight line passes a fixed point O with velocity 8 meters per second. So we have some point O, and when the particle passes that point, it has the velocity 8 meters per second. Its acceleration is a meters per second square. T seconds after passing O is given by, okay, so acceleration is given by 2t plus 1. First, we need to find the velocity at the point when t is equal to 3. Right, so we have acceleration. It's obvious that we need to integrate it. And so velocity would be the integral of 2t plus 1 with respect to time, and this would basically give us t squared plus t plus some c. Right now, here we know that when t is equal to 0, it should be 8. So when t is 0, the velocity should be 8. This is the reason why they gave us this particular value. So we just need to plug in 0. T equals 0, so this is 0 plus 0 plus c, and we know then when t is 0, this should be 8. In other words, c is 8. Right, so it's basically telling you that you start off with the velocity of plus 8. So we get our velocity function, which is t squared plus t plus 8, and their question was find the velocity when t is equal to 3. So at t equal to 3, velocity will be 9 plus 3 plus 8, which will turn out to be 20. So this was part A. Now part B says find the displacement from O when t is equal to 3. Now, the reason why they said from O is just to indicate that the plus C will be equal to 0. Because at time equals 0, it is at that certain point. And they're saying that at time equals 0, the displacement is simply 0. So let's integrate the velocity function, which is t squared plus t plus 8 with respect to time. And this would give us the displacement. This is equal to t cube over 3 plus t squared over 2 plus 8t plus some c. Now when we input t as 0, the displacement should also be 0. So 0 is 0 plus 0 plus 0 plus c. In other words, c is simply 0. So the displacement function is t cube over 3 plus t squared over 2 plus 8t. And if you want to find the displacement at t equals 3, this would basically be equal to 3 cube over 3 plus 3 squared over 2 plus 8 times 3, which will turn out to be 37.5 meters. And that's it. Right? That's all for kinematics.